I welcome to all on the course of refrigeration and air conditioning. I am Prabhupada Senapati, lecturer in mechanical department. Today I am going to calculate the COP of the ideal vapor refrigeration system. All of you know in the vapor absorption system you are using the low grade energy, that is the heat energy. But in the vapor compression system you are using the high grade energy, that is the work. Then you are coming to a nomenclature you are using here. So Qg is the heat is given to the refrigerant in the generator, and Qc is the amount of heat discharged from the condenser and also in the absorber to the atmosphere. Then Qe is the amount of heat absorbed by the refrigerant in the evaporator, and Qp is the amount of heat added to the refrigerant due to the pump work. So you are observing here the pump work is very less. That's why you are neglecting the pump work. Now you are applying the first law of thermodynamics. When you apply the first law of thermodynamics to the vapor absorption system, then we can modify the equation Qc is equal to Qg plus Qe. That is the Qc, that is the heat rejection, is equal to the heat addition to the vapor absorption refrigeration system. Then here you observe this, if you consider this is your vapor absorption system, and here is the Qg, the amount of heat you are giving to the system from the generator, and Qe also you are supplying the heat to the system, and here you are supplying the pump work, and the amount of heat rejected from the observer and from the condenser to the sink, that is the temperature T0. Then you are coming to the nomenclature you are used here, Tg, that is the temperature at which the heat is given to the generator. Tc, the temperature at which the heat is discharged from the atmosphere, from the condenser and the observer, and Te is the temperature at which heat is absorbed in the evaporator. So you are going to calculate the ideal vapor absorption refrigeration system. When it is ideal vapor absorption system, we can consider it is a perfectly reversible system, means there is no loss. Therefore, the initial entropy of the system must be equal to the entropy of the system after change in its condition. So we can write the Qc by Tg plus Qe by Te is equal to Qc by Tc. From the first law of thermodynamics, all of you know that the Qc is equal to Qg plus Qe. So we can modify this equation. Instead of Qc, we can write Qg plus Qe by Tc. Now we can write Qg by Tg plus Qe by Te is equal to Qg plus Qe by Tc. Now we will bring Qg one side and QE to the another side. We will keep the QG in the left side and QE in the right side. So we can, if you divide this equation, you can write QG by TC plus QE by TC. So from the right side we will bring to the left side, so we will give the negative sign. So you can write QG by TG minus QG by TC is equal to QE by TC minus QE by T. Now you can take it common the QG. When you take it common QG, so in the bracket we will get 1 by TG minus 1 by TC. Same thing you will get here when you take common the QE. When you take it common QE, in the bracket it will be 1 by TC minus 1 by T. So within the bracket, if you open, then if you calculate, then we will get QG into TC minus TG by TG into TC is equal to QE within the bracket 1 by TC minus 1 by T. If you solve, you will get TE minus TC by TC into T. So the amount of heat given to the generator, that is QG, is equal to QE. You will bring this part, this TC minus TG by TG into TC from left side to right side. So we can modify the equation. So QE into TE minus TC by TC into TE into TG into TC by TC minus TG. Now we can write QE TC minus T. Why you are minus multiply? Here you observe the evaporation temperature is lower than the condensation temperature, and the condensation temperature is lower than the generator temperature. So if you minus from lower to higher, the answer will come negative. So make it positive. You are multiply the minus. When you multiply the minus, it will convert TC minus T, and it will convert TG minus TC. So modify equation, you can write QE into TC minus T by TC into T into TG into TC by TG minus TC. Now here this 2 is multiplied, so we can cancel TC and TC from here. So you can write QE within the bracket, you can write TC minus T by T into within the bracket you can write TG by TG minus TC. So we can write the maximum coefficient performance of the system COP max is equal to output by input, and you are getting the output from the evaporation and you are giving the input to the generator and the pump. But here you are neglecting the pump work. That's why you are writing QE by QG. So QE, you will keep it QE, and QG instead of QG, just now you have calculated. QG is equal to QE into TC minus TE by TE into TG by TG minus TC. So QE, it will get cancelled. We will get TE by TC minus TE into TG minus TC by TG. Now you observe this T by TC minus T. This is the expression of the Carnot refrigerator when the temperature range is the TE and the TC. And this part, the TG minus TC by TG, This is the Carnot heat engine expression where the temperature limit is Tg and the Tc. So we can write the ideal vapor refrigeration system may be regarded as the combination of the Carnot engine and the Carnot refrigerator. So the maximum COP, you can write COP max is equal to COP of the Carnot into the efficiency of the Carnot. So finally you are getting COP max is equal to COP of the Carnot into COP of the Carnot heat engine. So this expression, it will helpful to you to solve the problem. So COP max is equal to TE by TC minus TE into TG minus TC by TG. Thank you.